Okay. Well, it's lovely to see you this evening. Thank you for joining us, and a big welcome to non-members for coming along to the meeting of Wombourne Scientific and Historical Society. We have our meetings every month, and we've been continuing throughout lockdown as well to meet every month. It's the third Thursday in the month that we meet at 7:30, and we've got a real good clutch of speakers arranged over the next few months. So hopefully you'll continue to join us for our meetings, and we look forward to actually being able to meet in person once again, perhaps, who knows, by the end of the year. But yeah, you're more than welcome, members and non-members alike. It's great to see you here this evening, particularly those of you who are watching us on YouTube. It's lovely to see you. We'll get underway in just a moment. First of all, a couple of parish notices for you. This is a notice for members of the Society. Our AGM is going to be held in March, and we'll be sending out notices of the AGM very soon. So look for those coming out in your email. All members of the Scientific Society Council are willing to stand again, but you're more than happy to put yourself forward if you'd like to stand on the council. Please do feel free to do that. Just let Alan know, send an email, and we can add your name onto the list. Obviously, the more that we get involved, that we get you involved into the council, that's the more involved you become with the society, and the more successful the society is. For those of you who are new to the society, we've got about 80 members. We've been running for 11 years now, or perhaps even more. Is it 11 years? Yeah, we meet, as I say, the third Thursday in every month, usually at the community centre. That's the library building in the village. Our next meeting is going to be on the 18th of February, Thursday, the 18th of February. And I'm hoping again that I've got that date right and didn't just make it up. Yeah, it's on Thursday, the 18th of February. So that'll be our next meeting, and we'll put notices out via our Facebook page. So just do a search on Facebook for Wombourne Scientific Society to find more information about that. I'm Simon Keeling. I'm the chairman of the society, and it gives me great pleasure this evening to introduce this evening's speaker, William Townsend. And I think, William, you don't mind by going by Will, do you?
No, I don't mind.
That's all right. Okay. And it gives me extra pleasure this evening because I've known Will for a very long time. In fact, I reckon since you were 2 days old, Will. I reckon that's when I first met you. Not that you'd remember that. And I followed his interest in physics very, very closely over the years. Will, as well as being a physicist, a budding physicist, he's also a gifted musician. An all-round, I'd say, is a very fine chap too. Having followed Will's interest in physics, it makes me really proud, actually, to introduce him as this evening's guest speaker. And I'm not going to tell you how old Will is, but sufficient to say that he hopes to go on and study physics at the University of Birmingham, if I'm right, Will?
Yes, that's it.
Yeah, and that'll be next year. So you can work out Will's age for yourself. And really, I think we are especially honoured this evening to have Will talking to us, because Will is at the cutting edge of research into physics, and he's going to go forward into a department of physics at the University of Birmingham, which is really at the forefront of current quantum research. So what we're about to hear is real up-to-date information from a young researcher with his whole academic career ahead of him. So what I would say to you is listen, enjoy. Will has a real gift for communication, and I think you're really going to get a lot from this evening. So without further ado, Will, I'm going to hand over to you. And just so that everybody knows, the way that we're going to do this is Will's going to do the presentation, which will last for 30 minutes or so. And then he's going to take questions at the end. But what I'm going to do is jump in, if I need to, periodically through the talk, if there's anything that Will perhaps hasn't made clear, and perhaps me with my simplistic brain haven't understood. So we've agreed that already, Will, haven't we?
Yeah.
and that's the way that we're going to play it. But if you have any questions as we go along, please type them in the chat window if you're joining us on Zoom, or in the chat window if you're joining us on YouTube, and I'll drop in the questions either as we go along or right at the very end. Okay, so that's the way that we're going to do it. So Will, without further ado, I'm going to hand over to you, ladies and gentlemen, William Townsend.
Hi everyone, hope everyone's okay. This is David and Goliath, how quantum physics answers the biggest questions. Now, physics is the study of anything physical and their interactions, and this can be from objects like grains of sand to planets, stars, and even galaxies. Now, it's because of this that physics is known for answering the big questions. Now, an example of this is gravity. It's what keeps everything on the ground, it's what makes the planets orbit around the sun, and what causes galaxies and the universe to have the shape it does. Now, it might surprise you to know that even though gravity acts on such a large scale, it's actually the weakest force. Now, when looking at quantum physics and physics at the smallest scale, we actually find that it deals with the strongest forces. Now, and funnily enough, the strongest forces, looking at this quantum, the small scale, can actually answer some very big questions. So the quantum physics, the small David can solve some of the big Goliath problems of the universe. So let's go into what questions we're going to be looking at tonight. So we're going to be taking the universe from a quantum perspective, that point of view at the smallest scale we can think of, maybe even smaller. And we're going to be asking, what is space? What is time? Then if we have time at the end, we're going to be looking at the Big Bang Theory, and we're going to rewind the clock to when the universe was actually the size of a particle. Now, let's get started and look at what quantum physics is all about. Now, let's go back to ancient Greece, and they came up with the idea of something being atomos, which is indivisible. And that's where the word atom came from. We later found that the atom can be split into more minute and smaller particles. But this idea of having something indivisible was put into use when describing all the interactions that we know. Now, I've shown all the interactions that we know of on the screen here. We've got electrostatics, which is your magnetism, what causes your magnet to stick onto your fridge. You have the weak nuclear force, which is radiation. An example of this could be Chernobyl. Then you have something called the strong nuclear force. This is a bit more abstract, but inside an atom is a nucleus. This is the core, the center of the atom, where the most mass is and the most substance of the atom is. And this contains particles known as protons and neutrons. Now, protons are positive, and what we know from electrostatics is that light charges repel. And to overpower this repulsion and to hold all the nucleus of the atom together, you have the strong nuclear force, which, like these circles binded together, it binds the atom together and overpowers that repulsion that allows everything we know of in the universe to form. Now, then we have gravity. Now, gravity is a bit of a wild card in the quantum world. We're not exactly quite sure what the description of it is at that small scale. We're not sure what the quanta, what that indivisible particle that interacts with us is and what it's doing with gravity. So we're going to talk about that a bit more later, and that'll take us right to the cutting edge research that theorists are doing now. So how would a physicist go about putting pen to paper? How would someone describe this quantum world? Now, Einstein was one of the founders of quantum physics, and his paper on the photoelectric effect, released in the early 20th century, again, a year later, he released his paper on special relativity, and this led to him winning the Nobel Prize. He actually founded some of the concepts of quantum mechanics, but he believed that everything that we know had to have a definitive answer. And later, what physicists known as Feynman and Schrödinger, who also worked on quantum mechanics, found out that the universe didn't work that way. The idea that having a particle in a room and saying that this particle is definitely in the center of the room, that idea was actually removed from everything. It removed and kind of left us in the unknown. That the idea of saying that something has a definitive answer was actually taken away from us. Quantum physics works in probability. So instead of saying that a particle is definitely in the center of a room, you would say that it's most likely to be in the center of a room. And let's say that it's less likely as you go to the edge of the room. So as you go further out from the room, it might be less likely. And as you go further to the center, that's where it's most likely to be. And it's this crucial concept of probability that Einstein didn't like. And he eventually said that God does not play dice. And unfortunately, Einstein was wrong. So let's explore this uncertainty in the Heisenberg uncertainty principle. And we're going to have a look. I was watching TV earlier and I couldn't find the remote. So I had to go looking for it. But this is no normal remote. It's a quantum remote. It is the smallest remote you can possibly think of. But the way I'm going to find my remote is that I know it's got batteries in there. So I know it has energy. So I can put detectors around my room to try and detect the energy coming from the batteries in my remote. Now, I've got some energy readings. I got some from under my bed, under the dog's bed, in my drawer, on my desk, behind my books. And I got the most readings from under my dog's bed. So this means that under my dog's bed would be the most likely place for that remote to be. And hopefully my dog has not destroyed it. Now, as we go further, now it becomes less likely as you look under my bed. And then the less likely place would be behind my books. Then it might become even less likely to be on my desk because I'm getting less and less energy readings. So it's most likely to be under my dog's bed, but it also could be in the other places. But it's this concept of this is where it's most likely to be that physicists in the earliest 20th century had to really grasp with. And this is how physicists plot positions of particles. They draw up a graph like I've drawn here to try and find where my remote most likely is, or where it most likely is, I should say. Now, I'm sorry, but I still haven't found my remote. So I'm thinking it might have been stolen. So I need to find out how fast this thief is going so I can try and catch him. So instead of taking one reading of the particle's position and where it's most likely to be, I take multiple. So I'll take one here, let's say one here. And because when I'm trying to find out the speed of the thief, I'm trying to find out the distance the thief is covering in a given time. That means I can calculate how fast he's going. But if I take more readings, and the more position readings I take, the better I know the speed. So let's say I take lots and lots and lots of readings like this top graph here. That means I'm much more likely to know the thief's velocity. But it's all with probability. All these points, all the peaks of the graph is where the thief is most likely to be. And it's this idea of probability that quantum physics brought into physics. Now, let's bring it together. This is an equation. Now, don't worry. I know maths is a very weird concept, especially when talking about such things like quantum physics, but it's actually quite simple. And we're going to break it down and talk about it. And you're going to feel really clever walking away today. So let's have a look at what's going on. I've actually given you a simplified view, and it's actually a particle's momentum, which is this Greek letter rho, instead of velocity. Now, momentum is anything moving that has mass and that has a speed, like a rugby player tackling another rugby player. The rugby player needs momentum to push the other player onto the floor and do the tackle. And then this x here is the position. Now, and these are linked by, this is just a constant. It's called Planck's constant, and we can ignore it for this evening. We can ignore the constants. I just want to come to grips with these two symbols. And it's really simple. You just multiply them together. And let's turn back to our graphs. So I know the speed and momentum of this thief really well. But the more readings I take, and the better I know the position, or the better I know the speed of the thief, I should say, the less I know the position. So the more I know the speed and the more readings I take, as you can see, the amount of position readings I have, there's no chance of me knowing the exact position. So the more I know the momentum, the less I know the position. And then the less readings I take for the momentum, the better I know the position. And it's this concept that physicists used when analysing the quantum world. So here's another equation, and it's not hard. We don't need to worry about the details. I'm going to break it down, and it's actually quite simple. We've seen this one just, and this one here is exactly the same, other than it's to do with energy, the E, and time. Energy can be thought of as an excitement. Now, particles, when they're really excited, they move really quickly, and they're buzzing about, they're vibrating, they're moving all around the room. But the less energy they have, the less excited the particle is. That means it's more likely to not move as much. And time, for now, let's ignore it. We're going to simplify the equation and just focus on the energy of the particle. And this is important because in Einstein's paper on special relativity, he produced the equation E equals mc squared. Now, again, it's a very famous equation. Some of you may have heard of it. And if not, we're going to break it down. Again, the E is energy, and the m is the mass of the particle. This is the amount of substance that the particle has, all the stuff that is inside that particle, all the actual raw substance and matter in the particle. And then this c squared here is a constant, and it's the speed of light squared, and we don't need to worry about it. All we need to know is that the mass and the energy of that mass is a store of energy, and that mass and energy are linked together. Now, it's that the idea that mass is a store of energy it's a very abstract concept, and the only time that humans have ever had to come to terms with this concept is in the nuclear bomb, because that's how they work. You get the raw matter, the substance, and you turn it into energy, and mass is a very big store of energy. So let's have a look at what space exactly is and what particles are making up space and everything we know. So particles can exist at many energies, and they have many purposes and uses. Now, force fields are carried by something called bosons, and unfortunately it doesn't work exactly like Star Wars. However many times I've tried to lift things up without touching them, like Yoda, and they work through bosons. These are force carriers, so they interact with what we know as matter and cause forces and carry forces. Now, this is a strange concept. This is a very strange concept, but we're going to break it down. So let's focus on matter first. And that's what we would know as stuff. Pretty much everything that is made up, any object that we know, tables, chairs, people, planets, stars, everything we know is made up, and everything we can see is made up of these matter particles. Now, the interactions between them that we spoke about earlier, like your magnetism, what's causing your magnets to stick to your fridge, what's keeping me on the ground as gravity, is described through bosons as force carriers. Now, these particles are all linked together by quantum mechanics, and it's their energies that cause them, and it's their energies that is actually in their mass, because it's the fundamental idea that Einstein brought into physics that mass is a store of energy. So all these particles that have mass actually have a lot of energy, and it's this that we're going to talk about when we look at all the different energies that the particles can have. You can have something called the W boson, which is a very strange name. It's a letter, and it just says it's a force carrier. It is something that interacts with matter and that causes the weak nuclear force, the radiation. And it's a very, very big, heavy particle. It's got a lot of mass. Then when we look at the electron, which is inside the atom, that has quite a low mass. And then when we look at a proton compared to the electron, proton is, again, very, very heavy. It has a lot of mass. There are a lot of particles making up a proton. So let's have a look at how this affects space and how exactly do these masses in space pull together. And that is through gravity. Gravity is the attraction of anything with mass or anything with energy. And as we've seen before, all particles that have mass have their own energy. So they are affected by gravity. Newton theorized gravity. He did not create it, but he did theorize it. And he came up with the idea that anything with mass is all attracted to each other. I have mass and I'm being pulled down to the earth, and because I have mass and because the earth has mass, I also am pulling the earth towards me. So let's have a look at gravity at the quantum scale. Let's break it down. And it's called the graviton, or at least it's theorized as the graviton. This is why gravity is the wild card, because gravity isn't known in quantum mechanics. It's not built into the theory. It is just pen and paper at the moment. We have no experimental proof of the graviton. However, I will talk to you about it a bit and say that there are some theories known as string theory and M theory, which do build gravity into quantum mechanics, and they do it in an incredible way. But it's through this that has caused it, and it's the concept of these theories that mean that it's actually extremely difficult to prove that gravity is part of quantum mechanics. And it's gravity that is the wild card, and it's gravity that we're not quite sure how it fits into the puzzle of quantum physics, because we may be able to put it on paper, but we have no experimental proof of the graviton and the gravitational particle. So let's bring all our particles together and ask what space is. Let's take, and again, let's take everything out of space. Let's say I have a box. I take all the air out of the box, so it's just empty space. So you could say there's no mass in the box. So there's no energy in the box, because mass is a store of energy. Now, but if we remember going back to the uncertainty principle, that you can't know the energy exactly. So that means that because I can't say that there is no energy, because that means I would know the energy. So there has to be energy in empty space. And it's made up of something called virtual particles. And these particles are bursting in and out of existence. They burst from energy into mass, then the mass bursts into energy, because mass is energy and energy is mass. They are linked together. So that means we get the idea of empty space. And empty space is actually full of particles and energy. So empty space isn't as empty as you thought it was. It is actually a swirling mass of energy. It is just a haze of particles popping in and out of existence, mass to energy and vice versa. It is incredible. And this is a very, very abstract concept, but I absolutely love it. It is incredible, in my opinion, that we might get a box and say it's empty, and it's actually full of empty space. So let's look at time. So we've looked at space and everything and what makes up space at the small scale, and it is actually a teeming mass of energy and particles. Now, how does this affect time? Let's think about what we know about time and because if you wanted to define time, it seems like a very difficult thing to do. If we all stopped moving, we would have no concept of time, because time is the measurement of change. For example, if I have a hot cup of tea, it eventually goes cold, fires eventually go out. So we measure change, and that is what builds this concept of time. So again, anything that changes, people who are young, they eventually grow old, and we can see that because they've changed over time. And it's this change that allows us to have this concept of time. However, we also have this constant flow. It's the change that makes time flow. We have this concept that everything is changing all the time. And this is what causes us to describe time as flowing. So let's talk about quantum time. Now, we've looked at space, and space is full of particles and energy, and it's constantly full of particles and energy. So it's constant in space, constant in time. So is it ever really changing? So does time exist at all when you go down that far? When you go down to the most minute scale, does the concept of time just go out the window? And funnily enough, if you go down to the most minute scale of empty space and see that swirling mass of energy, what we find out is that quantum time flows, and that you actually can measure the change in energy in empty space. And it's done through something called non-commutative von Neumann algebra. That is a big mouthful. And all we need to take from that is that there is a theory and a proven theory that show that time at the smallest scale can change over time. So time still exists when we go down to the smallest scale. And there's ways that we can do that. So what's the point? We've looked at time and we've looked at space at the smallest scale. We brought everything right down to the most minute scales that we can possibly bring it down to. So let's have a look at the universe on the biggest scales, and let's go back in time together and look at when the universe was actually in a quantum state, because the Big Bang Theory describes that, as well as being a very funny sitcom, it describes the universe as expanding, and it's still expanding. So when we go back in time, everything is closer together. So when we rewind the clock far enough, everything is the size of a particle. Everything we know, everything in the universe can be brought down to the size of a particle. Now let's look at this. This is discussed by Stephen Hawking. It was Stephen Hawking that that helped bring around this idea of the Big Bang Theory and really bring back the idea of rewinding the clock. And it's done through through cosmology. And this is a study of the universe at the biggest scales. Now, what happens when the universe is at the smallest scale? When the universe itself is tiny, when the universe is the size of a particle, maybe even smaller, what do you do? As a cosmologist, you're on your own. You're used to looking at big planets and galaxies, but now you're looking at a particle, but yet you're looking at the whole universe. So what would you do? Now, Stephen Hawking then brought quantum mechanics and cosmology together. And he did this through an idea of interference. Now, interference is something that stems from quantum physics. And it stems from the idea that we can't know the position of a particle. And we can't know and it stems from the uncertainty of a particle. And that we can't know how fast it's going, we can't know its position, and we can't know how it interacts exactly. That means you end up getting a pattern that looks like this. And in the middle is where that particle is most likely to be. It is the brightest spot of light. And as you go out, the spots get dimmer and dimmer and dimmer. And it's less and less likely for that particle to end up in that place. Now, this is what we call an interference pattern. Now, it's this pattern of light and dark lines that I want you to really try and picture in your head, and really try and picture that and bring it all together. So let's have a look at how this affects the universe itself. The interference pattern and the Big Bang. Now, when the Big Bang happened, the universe was the size of a particle. So in itself, the universe was in a quantum state, and it was a quantum particle. And this means that it was actually under the effect of interference. So every time you see a bright spot is where a little bit of matter would have been placed. Or I should say a little bit more matter and energy would have been placed, because energy is mass and mass is energy. So imagine that instead of having an even distribution of energy and mass, you actually have an uneven, messy, swirling chaos. It is chaotic. However, if we go back to what gravity is the attraction between all mass and all energy. And it's this attraction and these extra stores of mass and energy that actually caused mass to be pulled together. And it's this uneven messiness of the universe that caused galaxies to form and planets and stars and caused the universe to actually have the shape it does today. And it can be seen through going back to this really tiny scale and looking at the universe at the size of a particle, when the universe is under the effects of quantum mechanics and it's under the effect of interference. So now we know the distribution of matter and the distribution of space and what the universe looks like. Now let's look at time. And again, do not panic. We're going to be looking at some maths. Do not panic. Square numbers. And it is simple, but we're going to walk out here feeling like a genius, because it is actually really, really simple. Square numbers is a number times by itself. 2 times 2 is 4, and vice versa. -2 times -2 is 4. And this stems from the idea that if we get 2 negatives, you get a positive, and if you get 2 positives, you get a positive. Now, you can have the idea of something called a square root, which is this symbol here, and it is the opposite. So if I square rooted 4, I get 2, because 2 times 2 is 4. If I square rooted 9, I'd get 3, because 3 times 3 is 9. If I square rooted 16, I get 4, 25, 5, and so on. However, you always get a positive number. So you shouldn't be able to square negative numbers. And if anyone has a calculator and has it in a normal setting and tries typing in the root of a negative number, it comes up with an error. And that's because these numbers are what we call imaginary. Now, when you square root a negative number, it enters this realm of imaginary numbers, and they're complex, and it extends from this letter I. And it's a very strange concept, but it's useful when you look at the universe at a quantum scale, that time doesn't work in the usual way when you go down to that minute scale. The normal tick of a watch breaks down. The normal second actually loses meaning. The idea of time as we know it doesn't work. So physicists had to use these imaginary numbers and numbers that don't actually quite work to come up with the idea of time at the smallest scale. Now, they named it imaginary time. So let's have a look at something we've all probably done at high school. We've travelled the distance. So we look at how far someone's travelled, and we look at how long it's took them, time. Now, it always tends to be plotted with distance on the vertical axis and time along the horizontal. And you can get graphs. So let's say I was moving quite quickly, it would go up like that. And clearly, this person is staying still because they're not moving at all. However, when we use imaginary time, it doesn't work the same way as normal time. So it doesn't sit on this axis. Everything, or time itself, is flipped. So you have time as we know it along the horizontal axis, but you have the imaginary time using imaginary numbers that physicists use to look at quantum mechanics along the vertical axis. So how would you go about plotting this? And again, this looks quite complicated. And honestly, a lot of the arrows you can pretty much completely ignore. I want us to focus on this central sphere. So let's say time is going down here. This is time. And because time is going along the vertical axis, and space is also going along the vertical axis, then the whole universe is expanding along one axis. So it's expanding as a sphere. The whole universe is spreading out as a sphere. And this is what the universe looks like when at the smallest quantum scale, when the universe was the size of a particle. The whole space and time of the universe is plotted by a single sphere. It's captured in this ball. And this is a very strange concept, but I just think how incredible it is that physicists can sit and contemplate the whole universe inside a single sphere plotted by imaginary time and space. And that is the end of my talk. Thank you for listening. We've brought the universe together by using the smallest scale on quantum mechanics to answer the Goliath big questions of space, time, and the origin of the universe. Stay safe. Thank you for listening. And does anyone have any questions?
Wow, Will. Brilliant. Thank you very much. Thanks, Will. Wow. Well, I think I've got most of that. Anybody Anybody got any questions for Will? I've got a couple written down here, Will, but I'm sure we've got others as well. So anybody got any questions?
Yeah.
Yeah.
Will, what happened to the neutron?
So the neutron is, see, this was quite naughty of me because I wanted to keep it, I wanted to look at exactly what we needed in the nucleus of the atom. I wanted to bring across the concept of the protons repelling. The neutron is neutral, so it doesn't have any repulsion. So it doesn't,
But it's big mass, isn't it? Yeah.
The strong nuclear force does interact with the neutron and does hold it together, but it doesn't need to repel, and it's not dealing with the positive repulsion, the light charge, okay, because there's no charge on the neutron. So I decided to leave it out of the diagram just to
yeah. I just worried it had been renamed and I'd missed that bit. Thank you.
Oh, no.
Thank you.
The neutron's still around, I hope.
Yep.
Thanks, Linda. Anybody got any other questions for Will?
Will, I'm quite fascinated by this aspect of space-time, and I think it is used to try and explain how gravity works. And one of your slides showed a planet, I think it was Earth, with a moon circling around it, sort of distorting space-time, and that makes it appear that the orbiting planet is actually falling around the bigger planet. You recall that slide? I think it's the second or third slide. But what happens if the universe is down to one particle with an immense mass? What would be the shape of that distortion? The planet distorted a little bit like a trampoline, but if it was a bigger than anything we can imagine, would that be a cylinder without a top or bottom?
The idea of the universe when it's a quantum, when looking at the universe as a quantum particle, I always try and relate it to something we know, and we call it a singularity as that quantum particle, but that would also work singularity of a black hole. Now, the distortion of space due to a black hole is very similar to that of a planet or a star, but it's just amplified. That's how you get things like gravitational lensing, because the picture of space itself is being torn apart and warped completely, and it's just bending, almost not as a cylinder, but around the object. But the difference with the universe is that there's no space to bend around the quantum particle, because there's no space, there's no time, because it's all inside that quantum particle. So essentially, the gravity would be infinite, and it would be infinite warping of space, but there's no space surrounding the particle because it's all inside that quantum state.
So in that respect, that quantum particle is almost self-contained. It's got everything in it, and there's nothing else around it. Is that right?
It is completely self-contained. It is completely self-contained and self-acting. And it's that stems from the interesting idea of that the universe doesn't actually have a cause. The universe is. It is a self-contained being in itself.
Spiritually, that's quite interesting to me.
There is a problem, isn't there, with we know that relativity theory is correct, and that the speed of light is the governing speed for most items with mass in our sort of reality. But down at the quantum level, this doesn't seem to apply, and you've got this action to distance where the speed of light doesn't seem to be a constraint. And one of the big physics problems is marrying the two, because we know both theories are correct.
I've recently been reading around the subject of about uniting quantum mechanics and relativity, and it's one of the main ways that it's done, and one of the most well populated names, and one of the most well-known ways of of doing it is through string theory. And this proposal is taking the idea of a particle, and instead of there being a particle, it's actually a vibrating string. And it's through this idea of strings and how they interact with each other that gravity and all the other forces can actually work together to create a full image of the universe. But it's the problem that there's no experimental data to go with the theory. The theory works well, however complicated it is. But there's no full experimental proof, and that's the problem.
Mhm.
I think it's interesting there, Will, what John said as well about time, about how time breaks down. I think you mentioned that, didn't you, in the talk about does time exist at quantum level?
Yeah.
So do we then, I mean, going on from John's point, do we then have to think of time at the quantum level as not as still existing, so you still have time, but it doesn't conform to units that we know, and those units could be expanded or decreased as you go along the timeline, which may even not be a line itself? Does that make sense? I'm trying to work out how to formulate the question properly.
In relativity theory,
quantum level.
yeah. In relativity theory, time's not consistent. A satellite high in orbit traveling at a certain speed, time travels slower for it, which is why periodically they have to adjust the geostationary satellite clocks.
Yeah.
Otherwise, your satellite navigation will be miles out of phase or kilometers out.
Yeah. And does that, Will, is that breakdown of time at quantum level? Do we then include time within the equations at the quantum level or not? Is there anything there at time at the quantum level? I know you mentioned it in the talk. Is there anything there at quantum level to do with time that we can plug into the equations? Because it's not a constant, is it? It can't be a constant. No. You see what I'm trying to say? So how do we build it in?
Time can't be a constant, but away from time being a constant at the smallest scale, they use things like imaginary numbers that are strange mathematical concepts because it's not a constant, but it is a concept. Time is a concept, and it's used to look at speeds, and it's used to look at momentum, and it's the idea of time, imaginary time that can be plugged into the equations, and that allows time to be shoved into the equations so that people can understand how fast the particles go in, its momentum, and can use computers to analyze it.
Now you see, well, I thought I spent most of my days as a weather forecaster guesstimating things. But you've taken that to a whole new level. And in fact, Linda asked the question, a lot of it's theory, what's needed to prove it is correct?
Well, a lot of the stuff I tried to focus on with the three forces that we know of, which is a strong nuclear force, weak nuclear force, and electrostatic. And these are the proven theories involved in something called the Standard Model. It is the most successful theory ever created. And it is a theory about quantum mechanics, but it is gravity that we don't have experimental proof for. And it's because we simply put, we don't have the technology to prove gravity as being part of the quantum mechanics. And that we use colliders and to try and analyze quantum mechanics by smashing particles together. I think we had a talk a couple of years ago from Professor Evans of Birmingham University to us about colliders, and to the energy needed to analyze the universe at a quantum scale and analyze gravity at that scale. They say it's predicted, again, that it's predicted and not known, but it's predicted that you need a collider the size of the Milky Way to try and actually get all the energy to try and prove it. It's a very, currently we just don't have the technology to prove it.
Amazing. Will, just stop sharing your screen for me, would you? And then we can see you larger and we can see people asking questions. Brilliant. Thank you. There you go. There you go. Wow. And I love the idea of virtual, was it virtual particles? Fantastic. Brilliant. So the particle's not there, but it actually is.
It's a strange concept that something is there and not there at the same time. It's a very strange thing to, it's a very strange thing to try and get your head around.
Absolutely. Amazing. Amazing. Lisabella asks, how do we know that the universe is expanding as a sphere? Why not a square, or I guess for that matter, any other shape?
Well, cosmologists are trying to look at the shape of the universe because we're actually not quite sure when we look up at the night sky and we look at it in immense detail, we might not be sure. Are we looking at a mirror? Are we looking at ourselves? Does the universe fold back on itself? Does it fold? And we're not actually sure the shape of the whole universe, because what we know that when an explosion happens, everything moves away from each other in a spherical shape. And that's something expanding in space. But what does the universe look like expanding into nothing? It's a strange concept because we can plot things expanded in space, but we don't know how to plot an expansion into nothing. And it's a strange concept.
Is it actually expanding into nothing, or is it expanding into another universe? Oh,
I'm so happy you said that, because that is one of my favorite things to talk about, because there's so many unknowns and the uncertainty principle that we can't know exactly where a particle is going to be. Some theorists say that if we can't know that it's going to have the exact energy at that time, it actually does everything. A particle is going left, right, forwards, backwards, but it does it all, but each in a different universe. So let's say it goes north in our universe. In the universe next door, it might go south. In the universe next door, it might go west. And then the universe next door, it might go east.
Awesome. Get your head around that. So when we're going to sleep tonight, if that question pops into our head, none of us are going to be sleeping, are we?
We could well be expanding into a universe comprised of dark energy and dark matter, couldn't we?
Yeah. Oh, that's a really interesting.
God, John, I'm never going to sleep.
Well, look at it this way. I don't believe that in the singularity. If you take a collapse of a black hole, it's still got mass, it's still got gravity, so the Higgs boson is still operating, isn't it? So you won't have a point source. The Higgs will be there, giving the thing mass.
Wow. This is going to be a very late night. Excellent. Right. Well, I'm just going to ask you another one that's been on YouTube from ZXD. What do you think of let me start again. What do you think of the quantum model, and do you think it will ever be united with the standard model to have a universal theory of physics?
I'm gonna say that I think at the moment it's been done as patchwork. Let's say you start with a piece of, let's say you're trying to sew together some materials. You're trying to sew together a shirt, and you start with one patch of material, and to build the shirt and to make the shirt and sew it all together, you put in different patches of material, all of different colors, shapes and sizes, and we're actually just mapping it out, feeling we've got our eyes closed and we're in the dark, and we're just feeling out where we're going. We're not exactly sure of if we're going to get that theory and that single equation that puts everything together, but we're putting equations together that are linked, and multiple equations that map out the universe, but all in separate patches. So everything's linked together in a big map, but instead of being together in one equation, it's in a big map of equations. So it's all linked together in one big mapping of the universe and everything we know. But again, it's still theory, and putting that into experimental values is again very difficult. and we're not quite, and in some aspects, we're still not quite sure how to get the experimental values.
So do you think that there is something or more than one thing fundamental missing from our understanding? And I guess that brings in John's point of dark matter as well. Or is dark matter just a convenient polyfiller for physicists to get over a tricky question of where is the missing mass?
I think dark matter, I don't like the name dark matter. I disagree with the idea that there is missing mass. I prefer the name dark gravity. It is some unknown gravitational force that is pulling the universe and making galaxies accelerate faster than we know. However, we're not quite sure. So we give it the name dark matter. And personally, I believe that there will be a particle, whether it be WIMPs, which are weakly interacting massive particles, and I hope you love the acronym as much as I do. But I believe there are particles that could be built into the theory that could unite all the unknowns of the universe as dark energy and dark matter, because maths as we know it has got us this far, and I believe that it will get us further in the years to come.
Okay, brilliant. Thank you. Thanks for that. Anybody got any other questions?
Yeah. What's the most popular theory at the moment? Is it string theory or brane theory? Brane spelled B-R-A-N-E.
Wow, brane theory. Not heard of that one. Come on, Will.
Brane theory. So strings are one-dimensional. They are, and originally it was thought that strings are the most fundamental concept of the universe, that's as small as you can go to strings. However, there were 5 string theories. There were 5, and they tried to bring them all together. They tried to unite all the string theories, but that only worked when you invented something called branes. So instead of having something one-dimensional, you have something two-dimensional. So instead of just being a string, it's actually a membrane in itself. So, and this membrane unites all the 5 string theories, and it does it in theory. And I don't believe that hopefully in the years to come, there's experimental proof for string theory. But brane theory is just a higher level of string theory. It's a different form of string theory. And I believe that brane theory is the more advanced version of string theory. I think it was brought around in the 90s. And brane theory, I really think, will be the forefront of theoretical physics in the future. And I hope it is, because I think it is an incredible concept that you can unite so much so many mathematical concepts and 5 theories by increasing a string to a membrane. I think it's incredible.
Excellent. Thank you, Will. Does that answer your question, John?
Well, it needs an inspirational genius, doesn't it, now to crack this lot?
I think we could be looking at one.
Yeah, it could be Will. When Will gets over to the Large Hadron Collider,
that's right,
and dreams up another experiment, we might have the answer.
That's right. I'm putting a tenner on that. Brilliant. Anybody got any other questions for Will? I've got one here, Will. Just to round us up. Ben says, "Thanks for the talk, Will. What question about the universe would you most like to answer in your studies and career ahead?" What about that one?
Is a brilliant question. And if I had to pick something to study in the future, I hope to go into theoretical physics. I love maths, and I think it is the most amazing thing to study, in my opinion. It is amazing, but I think I would love to study dark matter and dark energy, because dark energy makes up over 60% of the universe, and dark matter is 24%. So everything we know is 5% of the universe. And to me, that is a massive gap. And theorists are working on it every day. You never know, it could be solved tomorrow. But I hope to study dark matter, and I hope to study the unknown acceleration of galaxies and the expansion of the universe. It's something that I'd love to work on, and I may not solve it, but I think I would happily be fulfilled in life to make progress in that problem.
Brilliant. Sounds like you're very clear on what you want to do.
I personally believe, Will, that there's no such thing as nothing. Nothing's an absolute. It's like -273 centigrade and all that. Probably never get to it. So you can't curve or manipulate nothing. So there was always something there to expand into anyway.
In space, I completely agree that nothing is a mute concept because of the uncertainty principle. Because we can't know the energy that there's nothing there, so it has to be that there is something there. So the idea of nothingness does go out the window. However, that's in space, and outside the universe as we know it, we don't know if there's space. So maybe outside the universe as we know it, there's something where nothing does exist, where nothing is a concept. However unlikely it may be, it still could be a concept in the unknown outside the universe and what we're expanding into. It may be nothingness, or it may be energy, it may be dark energy, or it could be dark matter. We just don't know.
And the questions just keep on going, don't they? And we haven't even thought about theological aspects of it yet either, when you're talking about nothing.
Well,
The start point, isn't there? You know, that's where all of that then comes in, doesn't it?
Well, we can't get down past the first picosecond.
No.
So it's mysterious beyond that. And if you want to believe in a creator, prior to that, there was no such thing as time. So he never had time to create anything.
And then we're on to, do you need time?
You never know. Quantum might work in imaginary time.
Yeah, exactly. Not if you can have virtual particles, John.
If we really understand time, we might crack space-time. Yeah.
Exactly. Anything goes. Well, I've got another question coming from Alan. What is a quantum computer? Alan's asking.
Now, a quantum computer works through data in a computer is built through ones and zeros, and they're known as bits. Ones and zeros are the information in a computer. And now, in a quantum computer, it's known as qubits. And because you can't know the state of a quantum particle, and you can't know if it's a 1 or a 0, a quantum bit is a 1 and a 0. So it can exist in all the states at the same time. So that means that you can process millions of pieces of data by using ones, and by having a quantum computer, you can process millions and millions of pieces of data, more than we've ever been able to process before, because we have a computer that exists in multiple states. So instead of just having a 1 or a 0 and having a coded computer, you have a computer that has multiple codes. That's what builds the computer. It speaks through multiple languages. It can be through ones and zeros. It can work in multiple ways and exist in more than one state. It's a very, very abstract concept. And it took me, I've been reading for five or 6 years on quantum mechanics. And it's only the past year or so that I've fully come to terms with the full impact and the full meaning of things in quantum mechanics. It's incredible, but is extremely strange and hard, and it's a very difficult concept.
Is that Google and DeepMind who are working on that, on the quantum computing? Is that
a lot of the big companies like Google is working on quantum computing, and it's just now qubits that I just spoke about, and that idea of a bit being a 1 and a 0, it can only exist in that state for so long until it has to decide if it's a 1 or a 0. Then it's a normal computer. The quantumness, that is not a word, but let's go for it. Quantumness has left the computer. So it can no longer work as a quantum computer. And I think the longest time it's worked for is just over a minute. And it can process millions of pieces of data in that time. But the longer and the more efficient we make them, the better it'll work as a quantum computer.
I think I read that it's of the order of billions of times quicker than existing computers. Is that? It's some huge number, isn't it? Some huge, unimaginable number.
In string theory, when they're trying to process data as we know it today, and some of the equations of string theory, they and some of the constants and the equations, they can plug them into a quantum computer, and the quantum computer can do the equation. Those equations would take a normal computer, like my laptop that I'm speaking to you on now, millions of years. And that is a very difficult thing to get your head around, on how weak our modern computers are compared to the quantum computers. And all I'm going to say is David and Goliath, the quantum can solve big problems by looking at things at the small scale.
Yeah. Wow. Feels like Star Trek again. Fidelio says on YouTube, I love the idea of how probability means it is probably impossible to have nothing.
It is impossible to have nothing as we know it in space. But again, we don't know what's outside. So you never know. It may be probable. We never know.
Yeah, fantastic.
Great question.
Will, you are a breath of fresh air, and you've put across a very difficult concept tonight in understandable terms. And I think, you know, if anybody can do that and people can get more than 50% from a talk such as that and understand it, you've done well. And I have to say, I kind of got more than 50% of it. So really well done. Philippa, are you all right offering a vote of thanks? I did send you a message.
Yeah,
I know this, I didn't ask you previously, but if that's okay. I'm just going to say one thing, right? I said to Will, this is like about a year or so ago, I said to Will, what are you doing at the moment? He says, oh, I've just finished reading a book. And I said, oh, what is it? And he says, it's Roger Penrose, The Road to Reality. Now, I've been trying to get hold of this book for quite a while. And that Jammy so-and-so there, Will Townsend, picked it up in Sainsbury's for £1. And I had to go and spend £30 on it. So it was just a bit of light reading, right? And that's it. And now, all these concepts Will's spoken about, instead of that blocking open a door, I'm now going to go and read them through. So thanks for that, Will. And on that note, I'm going to hand over to Philippa.
Will, I absolutely thank you so much. A brilliant, fascinating talk. And I got more than 50%, I think. Some of the imaginary stuff I'm not so good on because I'm a biologist, so it's a bit alien to me. But it was brilliant. And your enthusiasm for your subject shines through so much. I just think we're so glad to have you in the society at the start of your, well, just before your university career to come and talk to us. And I'm sure when you're professor, Will, you'll be back and we'll be lucky to have you then. John and Simon mentioned inspirational genius, and I think you are absolutely inspirational genius. And I know that we all wish you the very, very best of luck in your studies. And I just see you flying through everything. And as I say, being at the Hadron Collider and winning a Nobel Prize. There you go. There's something to aim for. But I think we are lucky to have you involved with us. And thank you so much. It's been brilliant. Absolutely brilliant. So I'm sure we all agree. So thank you very much. Well done.
Thanks, Philippa. Absolutely. And if you want to unmute yourselves and show your appreciation, please feel free to do that. Yeah. And well, I'm just going to say this one thing, one comment from Griff on YouTube. And thanks, Philippa, for that. Griff said, and Philippa mentioned this, we've had 2 Nobel Prize winner physicists from the University of Birmingham. Perhaps Will can be the 3rd.
Oh,
yeah.
And I think that sums it up.
Brilliant. Well done.
Absolutely excellent. Thanks, Will.
Thank you.
Thank you.
So much for having me as part of the society. I really appreciate this amazing opportunity, and thank you so much for letting me do this. I love physics, and I hope
No,
I get
Shows it's good.
we can tell, and it's brilliant that you do.
Yeah,
Thank you.
someone's got to.
Yes, I agree there, Linda. Yeah.
And Will, you've got a real gift for communication.
Yeah.
Yeah, that was really good.
Because trust me, you can't nurture that. That's born in you, and that's a real gift for communication. So keep that going, and it'll do you proud. Right, well done, and come back and talk to us. Don't forget us.
Yes,
No,
don't forget
yes.
us.
Now, listen, everybody, well, our next meeting is on Thursday, February the 18th. I've not got a title for you yet, but we'll get that to you as soon as we can. And it'd be great to see you there. Again, just a reminder about the AGM we've got coming up in March. We'll be sending out papers to members for that. But if you're a non-member and you're watching us on YouTube, it'd be great to see you as a member of the society when we're back meeting face to face. But until then, you're more than welcome to attend all of our meetings online and perhaps get to know us all a little bit. So, Will, thank you again. Philippa, thanks for the vote. Thanks. Thanks to all of you for joining us tonight. And Ben has just sent me a message to say next month's talk is actually on antibiotic resistance in medicine. So that's very prescient, isn't it? Very prescient. So next month's talk, haven't got the actual title, but it'll be on antibiotic resistance in medicine. So Will, again, thank you. Everybody, stay safe, get those vaccines going, and we'll see you next month. Thanks again. Bye-bye.
Bye. Bye.